Okay, we basically want to start this script with a double curved surface. So do you guys remember when we got to this point? We were probably like in the first script, in week 2's script, we would have a 4-point surface. Or what does Christina's script online have?
5 different surfaces. Sorry, it's a surface and then 3 points.
What is?
It's like a...
Is it like what I've drawn here?
No.
Yeah.
Oh, like, yeah, it is,
Yeah,
but
it's just more on
yeah.
5 seconds.
Yeah.
Okay. Well, we can either use this surface, like a surface and the points relevant to it, or you can use week 1 script. Basically, if you're using week 2 script, it's going to be around the point where we had the 4-point surface. So, for example, if I just build this quickly, I'm going to grab these 4 points. And we don't have a point here. So there's 1, there's 2, there's 3, and there's 4. And we used a process in week 2. I'll just hide this. I'll delete the surface. We don't need it. We had a process in week 2 where we drew a line, like a curve that followed the surface from the start point to the end point. Do you guys remember what that component was called? Or do you have it in front of you? No? We drew a line across the surface.
Oh, is that like geodesic?
Yep. So we want to create a geodesic line, and from there we got the midpoint to create that pyramidal panelization that we then use to actually do the finger jointing. So today we're going to create an inverted geodesic line, one that goes in the opposite direction. And from that we're going to generate surfaces that we can then use to laser cut and then bend into place. Okay, so we're going to be using this concept called a ruled surface, and basically a lot of the materials that we use in construction can only really achieve a ruled surface. So a really good example is paper. So if I've got a piece, that reminds me, I'm going to put on airplane mode so we don't get interrupted. Okay, so if I've got a piece of paper, and I try and create a hyperbolic paraboloid on it. So if I've got a 4-point surface, what's one way of creating a hyperbolic paraboloid?
Lifting up the diagonal corners.
Okay, so if I put my finger here, and if you put your finger on the other side, and do you mind help lifting one corner? No, lift that corner up. Okay, if you put your finger down, we're going to lift our points up. Do you see what that's generating? Is that a hyperbolic paraboloid? No? It's basically, generating 2 triangles, yeah? Because it really can't achieve double curvature in that surface, because for this to be able to actually create a hyperbolic paraboloid, it needs to be able to stretch. and paper doesn't really, or shrink, and paper doesn't want to stretch or shrink, okay? So, but we can actually achieve curvature in paper. We can achieve a ruled surface curvature, or a 1 degree curvature, which is basically in one direction, laterally, there's always a straight line. And the other direction, you can have whatever curve you want, okay? So, a cylinder is a ruled surface, okay? And a cone is a ruled surface, but a sphere is not. I can't make a sphere out of paper. Like a parabolic extrusion is ruled. So basically, if you can make something out of paper, it's going to be a ruled surface. Cool? We can go into the complexities of like ruled surfaces and their relationships with geometry, such that if you had a cylinder and you cut a plane through it, let me just demonstrate. If I had a cylinder and I cut a plane through it, like so, what type of shape would I generate? Right, if I were to cut a plane through it at an oblique angle, what type of shape would I generate? Exactly, okay? So there's some relationships that are generated by creating these shapes, but like if we go into that, it's going to literally take all lesson, and we don't need it. Okay, so what we're going to do is generate a line, a curve that goes from this point over here to this point. And we're going to do that using the same method we did in week 2. We're going to use a geodesic component, which takes a surface and 2 points. And so the 2 points that we're going to use are the points left and right. So that would be these 2 points in my particular script right here, but they could be different points for you. But the end result should look like this. By the way, just so that you're aware, if I draw lines, like I can actually create lines across this surface. Like there are straight lines on it, okay? But the reason that it's not a ruled surface, even though I can create straight lines on it, is because the relationship perpendicular to that line. Okay, so like I can generate a straight line across the 2 midpoints, yeah? So this line here sits on that surface, yeah? And if I were to take the quad and draw that across, that line also sits on the surface. But it's in relationship to the line in the opposite direction. Oh, let me just turn off grid snap. That's not perpendicular, okay? So they kind of need, we need, actually that's not quite correct, but if you have twisting, it's not going to be a ruled surface. They have to be either the same angle but rotationally, or they have to be parallel to each other. Cool? But so there we go. Is everyone at the point where we've got a geodesic curve?
No. Actually, I start
Have you got a surface like this?
We've got it like this from your book.
Yep. Okay. So see this 4-point surface. Create a new geodesic line. and you've already got a geodesic there, right? So use another, like create a new one and use the the alternating points to generate that geodesic line. Is that what you've done?
Yeah, so inner point and inner shift. That we
Who's not at this point?
yeah.
What have you got?
You know, in week 2 we created this hyperbolic parabola is reflected around
Yep.
a point.
Yep.
Is I can get a double one, but when I knock it back to a single, it just goes into this weird.
Okay. So there's who's using Christina's? You're using Christina's, and what have you got?
A surface, center point, support points, and external points.
The support points, are they the ones on the either side?
Yeah.
So I would just use the surface.
Yeah.
Like imagine this is now the surface, yeah? And plug that into a geodesic and plug your 2 support points into S and E.
Also get rid of this 4-point surface.
Don't you use the 4-point surface? Oh yeah, like sorry, you can either use this or reference the surface from Rhino or use Christina's surface.
Supports S&A.
Yep.
Central comes out of 4-point surface.
You don't really need central, I don't think.
And so
Mine don't cross.
Pardon?
Mine don't cross over the shade.
Can you chuck it on USB? Thanks.
we're just going to work out that one.
Yep. Because that way it'll work. So I think the point here, one of the points here is that like even though we're working on different scripts, this process should be able to work on all of them, but you just need to make sure that your inputs and outputs are like matching up. So it's going to get a bit difficult once we start sort of diverging and doing different forms and shapes. Time to do the USB superposition.
Zero grasshopper. It's a file, folder. Yeah.
Oh, that's you. That's not what Christina's script was.
Oh no, I was.
No. Could someone pass me Christina's script with the USB? Or does everyone have this?
No.
Can I get Christina's on a USB?
Can you pass the USB on?
Okay, while that's happening, I'm just going to keep explaining what's going on in terms of concept. If we take any shape, whatever the shape is, and we create a surface that goes to a point, such as this. Thanks, mate. Then the resulting surface should always be a ruled surface. Okay, so that means we can unwrap this and make it out of paper. Okay. So, like, those the way that I was rolling that cone up, right? There would be a way to cut the paper out and then form it into shape so that it would then end up creating a form like this. Cool? Okay, so what we're going to be doing is taking this curve, and generating a surface that goes to these points. And those two surfaces can then be unwrapped and then placed, like cut out and then reformed to create that shape. Okay? So that's what we're going to be doing today. But we're going to be making it out of plywood. Has anyone tried to bend plywood into shape? No? Do you think it would be difficult? Slightly? Okay, so what we're also going to be doing is generating something to do to that plywood to help make it weaker so that we can actually bend it. Cool? Okay, so let's get Christina's starting script. Logan didn't put it in Grasshopper. That's okay. Thanks, mate. Okay, so what we're going to do, just like last week, we're going to work on just one surface. And Christina's display is ugly. Okay, so we're just going to work on one. So we're going to use list item to pick one of those surfaces out. Then our support points, okay, I can see what she's done. So we only want, if we get the first set of support points, like the first item, it's going to be the one on the right. And then if we just click the little +1 on the list item, that's going to give us the second point to the left of that surface. So now when we use geodesic, so let's go grab the geodesic, we plug our one surface in, we plug our start and end points into that, and we end up with our nice little parabolic outcome. Okay, are we all there now? Yeah, if you go File, Preferences, you can then, under Viewport, you can grab the default and just drag that down onto Christina's super opaque red thing. Huh?
I can actually see.
Yeah. Cool. Okay, so it's actually quite simple. The difficult thing for us today is going to be creating a 2D surface that represents the 3D object. But we'll get there. So what we need to do is generate a surface. So we're going to grab the extrude point component. We're going to plug our geodesic curve into the base, and we're going to either use the center point or the external points. So let's just use central point, because there's only one of them. If we were to use the external points, it's going to generate a surfaces that look like this. And that's because there's more than one external point. So if we use external point, just make sure that you have a list item which picks out the first one, so that way it's generating that. So I'll just leave that there and we'll work on central point for now. And you can see this is rather, like, it doesn't actually represent that hyperbolic paraboloid too well, but it's close enough. Okay, how do we get this to be flat? There are various plugins that will unwrap a surface for you, but I don't want to use them. We're going to do this vanilla. And basically we need to create some form of approximation of this surface in 2D. And this is where it gets a bit difficult. So if I were to just take this surface and look at it, it's actually, like the way that it's made up, if I were to divide my geodesic line up into points, I can then draw straight lines that go from those points to the center point. And those lines effectively make up that extrude to point. Dude, there's a C here. Yeah. Okay, so these lines, they like if I loft them now, I'll get the same surface. There's a chair there. Plus, last time we did the lessons, everyone was sitting in groups of 3 per table, but there's some tables that are just 2. So, like, we can squeeze 3 people per table in if you want to get closer. Cool, or not? Oh, we are. But yeah, you could probably sit in this table. There's space. Cool. Okay, so like this extrude to point is practically the same as drawing lines and then lofting. Okay, and no matter how many lines we add to this, so if we make this 50, then we still end up getting that same outcome. Okay, so we now have to somehow translate this 3D geometry to 2D, and the only way I can think of doing it without using a plugin and fast enough that we can get through it by the end of this tutorial is by measuring, this is going to be messy, is by measuring the angles. Is that going to work? He's hoping that it'll work. Okay, so by measuring the angles between each of these lines in 3D, and then creating the same setup in 2D with those 2D angles, okay? So if you've got, like, you have to imagine we're taking a triangle in 3D, yeah? And then we're gonna draw that same triangle in 2D. And so as we draw the triangles in 2D, it'll create an unrolled version of this object. Does that make sense? So, to measure angles, we're going to need to generate vectors. And by the way, this is going to be the difficult thing about this particular lesson. It'll get easy, like, this is just getting us to the point where I can then talk about the patterns required to make the living hinge to actually bend this thing. But we kind of have to get through this super difficult thing. Just like last week, we had to do like weird fucked up finger joint angles and stuff like that just to learn how to do finger joints, okay? So this particular part, very difficult. If you just follow along, I don't expect you guys to super understand, but if we get through this, then we can talk about the living hinge stuff. You look like you're like...
Yeah, well, mine's not quite working, but I'm still...
Okay, where are you at? Where are you at?
Well, it's coming out instead of coming out the centre point at the top, it's coming out the bottom.
Yeah,
from
mine's
the
on.
centre point.
Huh? Instead of coming out of the center point at the...
Imagine your centre point's up, we've raised it up,
Yeah.
it's coming out directly below it.
This using this center point.
Yeah.
What? Serious?
Yeah.
It's almost like instead of
Are you using
being
Mac?
like that, it's just gone like that.
Are you using Mac?
Yeah.
So does the surface look like this?
Yeah.
But your center point, if you preview that, that's on the floor.
Yeah.
Okay.
Just that's where it's coming out of.
Um,
Hang on.
Yeah, mine's on the floor.
Guys, can you see that little bit of the script?
yep.
I think I'm running.
It's pretty much in the same thing, but it's just like just tilted it like that.
Okay. Well, see this. You can grab this surface. After grabbing this surface, we use list item on that one surface.
Yeah.
Okay. Then we can use deconstruct brep on that surface. That'll give us all the points, the edges, and the face of the surface. Okay. So with that, we can then use the list item on the vertexes, and with that go 1, 2, set it so that it goes up to point +3. Fortunately, the eye, so the first index is the center point. So what we're going to do is use the +1 and the +3 for the geodesic line, like so. And then we can use the eye and the +2 as the point to go to. So in this case, I would be going into P for the extruder point. I will also go into the line component which generates those lines. Okay, have you done this? Deconstruct brep.
That's where I'm at.
Have you used list item?
Yeah.
Have you added the indexes to it? Huh? Do you understand what I'm doing? So
Yeah,
instead of using these points, we're extracting the points directly from the surface. Okay, by deconstructing it, we get each of its vertexes. We then get the indexes of each, like we pick out the first one and then say, okay, we don't just want the first one, we want the second one, third one, and fourth one. You're shaking your head?
No.
You don't get it?
No.
I'm way lost.
Have you got deconstruct brep?
Yeah.
Have you got the list item
Oh, my deconstruct here is coming out the wrong thing.
coming out? Yeah, you want vertexes. We'll get there.
Okay. Deconstruct into the list.
But, huh?
The script from when we first did it, not
Yeah,
one from
it works, right?
But then it's because when we originally did the thing, we moved our original point up. So then why don't they just take the point that we moved up?
Because they're not using. For some reason, theirs is flat. I don't know. Like this is the fail safe. You can't go wrong with this one. This one has to work. So basically, like if I get rid of all this, okay, if we only worry about geodesic, right? Are you generating your geodesic line now?
I was always generating the line.
Yeah.
Okay, so now we've got I and +2, yeah? These are going to be the points that we're going to use to generate the ruled surface. So if I divide my geodesic curve up and I create lines, if I create them from I to P of the divide curve, I should get these lines on.
No, mine's just crashed completely now.
It crashed.
Well, not crashed, but it's just everything's gone red.
Are you using Christina's script?
Yeah.
If you go File, Preferences,
I got it.
go File Preferences,
Yeah.
go to viewport and drag this red thing into the bottom red thing. Okay, and then close. Can you see it better now? Oh, you mean that went red?
Yeah, yeah.
Well, you're plugging a point into the surface.
Right, so that wants to go.
So if we're working on a surface, which surface are we working on?
The first one, so
This one. Yeah. So, dude. If you're going to follow along, it's going to be a lot easier if you do that.
Okay. Yeah.
Cool, because it's basically like if you're visually just going to follow along, it's probably easier to do it with that. So plug that into your
So
the
plug
surface.
that in,
Yeah.
there.
Yep. And your geodesics are going to be generated. I'm guessing you don't have a mouse.
No.
Your geodesic is going to be generated there, like so, but then the point that you're going to generate that to is that point.
Right. Okay.
Okay. The reason it's flat is because you're using the support points, not the center point. Yes.
I'm not quite sure why this in this shape the curve is under the surface and it's like this.
Because the surface that you're using is the quality that you've set it to is like the worst quality possible.
Oh.
Okay. Yes. What are you asking me? Is this correct? Is that what you're asking?
Yeah.
Yes, it is correct. There's your... Geez, I don't understand why you guys don't come with mice. Like, it would drive me insane to do this with a mouse pad. Yes, it's looking okay. Okay, man. Just look what I've done. See your list item.
Yeah.
How many outputs does it have?
2.
No. How many outputs does list item have?
It's got 3.
It's actually got 4. Yeah? So we're at plugging +3 into that, not +2.
Still coming off.
Yeah, yeah, you're having the same problem they're having. Why? Better? Okay. We're there. We're not even at the hard part. Okay. So what we need to do, when we want to measure angles, the only way we can measure angles in Grasshopper is with vectors. So instead of, like, these lines are effectively things that we're going to use to visually represent a vector. At the same time, we can generate a vector 2-point. So that works just like a line. You plug your points that you want to generate the vectors from, and can I just be really mindful of what's being plugged in where? I'm plugging the I, or the central point, into the A, and then I'm plugging the divide curve points into B, Just be really, like, a lot of the issues that I've seen on each of the computers just now was just people plugging in the wrong output into the wrong input.
Do we get rid of, is loft gone? We got rid of loft?
You can leave loft. You can leave it. You don't have to get rid of it. Okay, so by doing that vector 2 point, what that's generated is a number of vectors. And to measure, we just want to measure the angle. Is this the right way to do it? I think it's the right way to do it. Okay. We just want to measure the angle between the first vector and the second, and then the second vector and the third vector and the fourth, etc., etc. Okay? So we're going to use the component shift list because it actually does something other than what I've taught you guys. In that we remember when we had a circle, yeah? And we had everyone see? Cool. When we had 4 points, I'm going the wrong way, but whatever. When I want to shift that list, if I shift it 1, the lift plus 1, the lift will shift like so, and therefore 0 comes first on the right here, then 1, then 2, then 3, yeah? But that's only if we're using the wrap list. So if here I've got wrap set to true, if I then set that to false, then that's kind of treating a list like this, 0, 1, 2, 3. So if I shift that list, I'm getting a scared look. If I shift that list 1, what happens to 0? So that's now 0, that's now 1, and that's 2. What happens to 0? Well, no. So imagine like this is wrapping it. It's like a circle. So when we don't wrap it, 0 disappears, okay? So what we're going to do is take our vectors and shift them 1 with the wrap set to false. And then we're going to shift them -1. So I'll just use a panel just to show what we've got plugged in here. So we'll have -1 as one of the shifts and 1 as the other. And with that set to false, it now is going to create like an offset list for either. Okay, so what we've done is we've gone, okay, get rid of the first item from the first list and get rid of the last item from the last list, from the second list, sorry. So then it'll create a relationship like this. Right? So if they're the same list, it therefore creates a relationship between like the consecutive elements of that list. Cool?
Scroll up just a tiny bit so I can see what you've done.
So I've plugged the vector into the shift list. The 2 shift lists.
When I connect the divide curve to the B on both ports of the line and then the vector 2 point,
Yeah.
it then removes the lines.
Removes them.
Yeah. But where'd you pull the A from?
The A is the center point, which can either be I or use I. Yeah, see this, man?
Yep.
See what you've done? Can you explain what you've done, like what you've done?
So you connect.
No, look what you've done, okay? So I've got, guys, just look at what your cables are doing, okay? So if I've got a component that's outputting a point, yeah?
Yep.
And I've got a line component, A and B, what does it take to draw a line in this case?
2 points?
2 points, right?
Yeah.
So the first point is going to be A, yeah? And the second point is going to be B. Right? And that draws a line, yeah? Now, what if I put that same parameter into both A and B? Where's A going to be?
On top of each other.
Yeah. So what type of line is that going to generate?
One of no length.
Yes. Okay.
Yeah.
So just look look at your scripts. Look at what you're doing. So the A, plug I into the A. Yeah. Cool. Is that working now? Okay, so is everyone at this point? Almost? We'll get, so what we're going to be doing is measuring the angle between the two vectors, okay? So this guy here, the angle component, it does that. And by default, if you don't plug a plane into it, it takes the two vectors and uses that as the plane. Okay? So what does it take to make a plane? Like if we think of planes, what do they have? They have an origin, yeah? They have an x vector and a y vector, yeah? And so if we're just plugging two vectors in, you can quite easily generate a plane off those two and then measure the angle between them, okay? If you want to measure the angle relative to another plane of two vectors, like if I were to have two 3D vectors and I just want to measure what their rotation is in 2D, then you can put the plane that you want to measure that to into P, and that'll give you the outcome. Have you caught up?
I think yeah.
Cool. Okay, so what we're going to do is plug our two shifted angles into the angle component, and the output of that should give us the angle in radians. It's been a while since you've seen radians, yeah? No?
No.
You just saw them recently? Okay. Cool. And so if we go to the math component, the math tab, and we grab the degrees component, if we plug the radians into that, that'll just tell us, okay, we've got 4.75 degrees, 5.59, 6.5, blah, blah, blah. Okay? Cool. So this is gonna.
What different degrees do you?
That's okay.
Yeah.
That's fine. Cool. Okay, and then the opposite of that, the reflex angle gives us the, whatever we just drew, minus 360 degrees, basically. We don't want that one. We want this one. Cool. So what we're going to do is we're going to draw lines that represent these in 2D, and then we're going to rotate them relative to the angle that we need to get a final flattened surface. Okay? So to do so, we are going to now draw lines from the start point. And I'm going to use a component that draws lines a very different way to the way that I've been teaching. So what's one way to draw a line?
2 points.
2 points, yeah? And you draw them between the 2 points. Another way is if you have a starting point, a direction, and then a length. Along that direction, we can then draw a line, okay? So if you don't necessarily know where the end point should be, but you at least know which way you want the line to go and how long it should be, then we can draw a line. And I think that's kind of a method that a lot of people use to draw lines in CAD, yeah? You have your start point, you then you just put your mouse in the direction that you want to go, you type in the length that you want it to be, and then it draws your line, right? Yeah? Cool. And then if you want to do a 2-point line, you snap from one point to another, yeah? Okay, so what we're going to be doing is drawing lines in the x direction. So let's use unit x. You can find that under vector. That's very much like, it's just like, whatever you plug into that, it's going to go in that direction. Cool. And then the final thing that we want is we want to draw the length. And the length of our line is going to be, I'm going to press F7 so that we can actually see this on top of the grid, with no grid, sorry. See here we've got, with the 2-point vector, we've got a V, which is the vector, and then L. That gives us the vector length. So we can actually use that length to draw our lines. So what that will do is produce 10 lines, each with the same length of the lines in 3D, okay? We now need to rotate these lines relative to these numbers, okay? So there's 9 lines, there's 9 rotation values and there's 10 lines.
Can I ask a silly question? Well, how does it know we've taken the centre point? Because we've not plugged anything into it.
Pardon?
We've not plugged anything into that construct point.
Because the default for X, Y, and Z is 0.
Okay.
So if I mouse over X, it says 0. If I mouse over Y, it says 0, and Z says 0. So by default, it's origin.
Right, okay.
So it's just a little cheats way of quickly getting origin. You just drop a construct point in and it's done. Cool? You can put this point wherever. So we can actually use this point over here if you want, but it's just quick and easy, right? Cool? Okay, so if I use transform and rotate right now, and I rotate these points by the angle, and let's not use the degrees, just let's use the angle, we're not going to get the appropriate shape. Okay? This definitely does not equate to this, yeah? We can all quite plainly see that, yeah? So, can anyone have a guess why?
Choosing the wrong plane or something?
No. Do you want me to have a go? Should I say? Just to save time? Okay. What we're doing right now is we're measuring the angle between each of these lines, yeah? So we're getting the angle between this one and this one. But when we're rotating these, it's rotating from the origin angle, yeah? So what we need is, this is gonna be fucked up. What we need is for this line to be rotated plus the rotation of the first line. And so the fourth line is going to need to have the rotation of the first line, second line, third line for it to be in the right place. Does that make sense? Yeah? So we actually have this cool little maths function. It's a bit different to the other operators, and as well, it's one of the operators that we can't, I don't believe we can replicate it in the expression, and that's mass addition, okay? If we use mass addition, if we plug our angles into that, and then we get the result, it gives us all of those numbers added together, okay, as a final number. But what we can actually do is look at what happens to those numbers as they get added up, okay, which is coming out of the partial results. So what that does then is gives us the first number plus the second number, that then resulting plus the third, then resulting plus the fourth, then resulting plus the fifth, etc., okay? So if I then plugged that partial result list into A, we're starting to see our lines actually start spreading out the way they should. Okay, but there's one issue. How many lines do we have and how many rotation values do we have?
10 lines
And-
versus 9 rotations.
Right, we actually have 11 lines and 10 rotations. Because remember, we've got 0, yeah? Huh?
I've got 84 lines and 83.
Okay, that's just, you
I don't
just,
think it makes a difference.
no, yeah, it's just one is less than the other, right? One is one less than the other.
One less than the other, yeah.
Right, so what's the, like we're rotating our first line by a number, right? But we should actually be not rotating the first line. The first line should have 0 rotation, and then every line after that needs to have that corresponding rotation, yeah? So we can use merge. Have I shown you merge? Yeah? So we can use merge, and merge will just basically, if we plug our partial results into D2, and then we plug a nice integer, sorry, actually let's just do that with a panel. We plug a 0 into the D1, then what that'll do is hopefully create a list between the two. And this is where it gets, I get to show you something a bit fucked up about Grasshopper. Okay, so when we do that, most of us are going to get a result like this. If we plug it into a panel, we're going to get this weird dark band, which will have the number 0 in it, and then another band with a whole bunch of zeros in that band, and then the rest of the numbers. Is everyone getting that? Okay, so what we're actually seeing is Grasshopper's way of managing data, and it gives an address to that data. And in this case, it's assigning, as we've been working with these components, it's been assigning new layers to the data structure for our angles, and we want to destroy that, okay? It's something that we'll get into later. We'll be able to explain it more. But in this case, to destroy that data structure and make it the same, homogeneous, we need to right-click D1 and select flatten, and then right-click D2 and also select flatten. That'll flatten that data structure and force them into the same list. And then once doing that, you can plug that into the A, and that should complete the rotation. Cool? So we've kind of made an approximate two-dimensional layout of this three-dimensional object, okay? The more lines you use, the more accurate it will be, okay? So right now we're using a very, like for example, we're using 84. Yours is 8 times more accurate than mine, we'll say. Okay, exponentially, the more lines you add, it'll get closer and closer to being accurate. So as I divide my curve up, let's say to 50, the approximations get more accurate, and to the point where this is probably, accurate enough. I don't need to get any more accurate than this. Cool. Now we're only using based on some of the models I've seen, you don't have to be perfect, okay?
So how did you change the amount of lines there?
I right-clicked N, set integer, and then typed 50 in. But you can also use a slider. So yeah, we could say 0 to 50.
Right-click N.
Yep. That's me. That's my habit of just using fixed values. You can also put a slider into that thing. Okay, so we are going to create a loft from this now. So if I plug loft in to our rotated lines, we should get a nice lofted surface. And it's the if I then plug that loft into a curve component, I think for the Windows users or for everyone, if you plug that into a brep edges component, that will then give you the curve outcomes you need to laser cut that shape, okay? But we have an issue. If I plug this in, if I just chuck this onto a piece of plywood right now, 3mm plywood, I'm gonna get shit, right? I'm just gonna get a piece of plywood and I'm probably gonna have to snap it for it to actually bend back into the shape that we had, yeah? So we now need to start working on a process. Pardon?
Yeah, same on mine.
Your loft came back with an error? Can I see it? Just mount. Guys, just make sure at the beginning of your script we want to pick out one surface, just one.
How do we do that?
Use a list item. Plug your list of surfaces in.
So when we did ours, we just had
4.
yeah.
Yeah, but we're going to just work on one of those 4, because if we do whatever we do to one, it can be repeated 4 times.
Right.
Like when we build it, just like what we did last week. Yeah. Yes.
I got a line that like project to another direction.
Pardon? You have a line.
Yeah, they like go into another direction. Like these are like most of them that go this way, but they get
One shoots off into the middle of nowhere. Ooh, that's an interesting one. You haven't, you've got this. This also needs to be set to false. Both need to be set to false, man.
Still doing the same thing.
Huh? Sorry, let's fix this up. So we're going to just work on one, yep, and we also want to work on 1 and 1. Better? Excellent, and that needs to be set to false.
My line actually don't count that.
Pardon?
The line is on the flat pane.
The line is what?
It's not counted out.
Is not.
Because you do have the lines on the XY.
Here we go. Hang on. So we're just going to work on one surface
Yeah.
and one set of points. Oops. Cool. Then you've plugged the one rotation in when we want all of these. Cool? But we want that going into there and that going into there. And that will then generate that.
Okay.
Cool?
So can I ask you, how come we didn't have to do, you know how last week we had to shift the shape flat?
Yeah.
essentially? How come we haven't had to do that?
Because
Is that what we did with the lines?
we've made, what we've done is if we took this 3D curved shape and we shifted it onto the 2D plane, it's actually still going to be curved, right? The process of orienting doesn't like if I take this and then orient it, it's not flattening it out. So what we've done is we've made a process that measures the object that we want to create and then recreates that but in a 2D environment. Yeah?
Yeah, that's, yeah.
It's actually rather complex process. Fortunately, we're only doing it with one surface, so we can generate that. But if you've got like an object that looks like this and you want to create a script that then flattens that out, you have to start making some really weird geometries to do that. And in this case, we're relying on the fact that it is a ruled surface. So we can create triangles across a ruled surface, measure their angle, and then lay them out in 2D. But with a non-ruled surface, it doesn't work. Okay? Are you good? You look good. You look like you've solved yourself.
Yeah.
Excellent.
So that the origin of the vectors need to be below the central point.
Pardon?
The origin of the vector.
It can be wherever you want.
Okay.
Or just go to another way.
Yeah, it's not on the below of the shape.
Yeah.
That's fine.
It's fine.
Your shape's over there, and we're remapping it to the origin. It's fine. Okay? That looks good. That looks good. We all look good. Okay? Yes. You have a question? Sorry. What we've done, just to re-explain, is we've taken a shape like this, yeah, in 3D, and then we've gone like that, okay? Hey man, whoa! Jeez, tripping out, man. What are we doing? This all looks good. I'm not helping anyone in the future if you don't have a mouse. Like, can you plug that in, please? It's just the most frustrating thing. Especially all of the, like, everyone's mouse pads have different, like, gestures. And it's just, it takes me forever just to get used to it. And then, ooh, what's going on here? Hang on, don't. Yeah, that looks good.
No idea what this comes from.
This one. Yeah, that looks fine, man. You've just got some surface over here somewhere that's all screwed up. Keep working on this.
Okay.
Cool?
Thank you.
No problem. Okay. So we're going to use a process that we keep referring to as living hinge. And it's this idea that comes from industrial design whereby if a hinge normally, like we look at these doors, the hinges of the door is something that's added, like it's attached to the door and then the frame, and it's a thing that allows you to rotate and pivot on that hinge to open and close the door, okay? A living hinge assumes that you have an object that opens and closes, and that object's hinge is actually the same element as both the thing that you are opening and the thing that it is closing. Okay? So some of us are probably old enough to remember like Kinder Surprise or Yowie. Do you remember Yowies? Or Kinder Surprises? Okay, do you remember the little egg thing that, like the actual little plastic capsule, and you would open it and it was made of two parts? That chokes, like if a kid puts that in their mouth, it chokes them. Yeah? So what they've ended up doing is making that little capsule now. I think that's why they banned it in the US or something like that. They now make that little capsule like so, with the plastic is actually part, like there's a little hinge that allows the capsule to open and close but keeps the two pieces together, and it's actually made of the same plastic, okay? And so what they're doing is relying on the flexibility of the plastic to actually hinge the element. That's a living hinge. So it's a hinge that the material itself allows you for that rotation, yeah? We're going to use a technique that allows us to make living hinges out of timber and sheet material to actually just generate curved objects, okay? And the process, actually, I'll just bring it up on the screen. How long have we got? We've got an hour and a half. Excellent, we've got plenty of time. So, and look at that, even just by typing living hinge in, we start to see some laser cut plywood results. I don't even have to type plywood living hinge anymore. That's good. So what we're doing is we're basically going to cut away from our material elements that then allow it to bend, okay? And we're also going to, this is a concept that works quite well with timber and other materials. Do you remember this guy? The parameter tester explanation thing? If we think of, like, you all know what the inside of this looks like, yeah? If we look at it from the side, we get the little corrugations and there's cardboard, and in plan, those corrugations sort of run in a line, yeah? So this is a very strong object in the direction of the corrugations, but then I can quite easily form it into a curve in the opposite direction that those corrugations are traveling, yeah? The same applies with timber. Those of us who actually make models, I'm quite sure you've dealt with balsa wood. So if you have balsa wood and you take the grain in one direction, then that balsa wood's going to be flexible in this direction, and it's going to be really strong in the direction that the grain is going. Yeah? Okay, same with meat. Just remember this is a nice little trick. If you're eating steak or cooking steak or whatever, making a steak sandwich, look at the grain of your meat, yeah? And cut the meat opposite with the knife, so that your teeth only have to cut up the little bits of the grain. Cool? Pro tip with cooking steak and meat, yeah? Because the grain is the strong bit. It's the bit, like in our muscles, it's the thing that goes along, and it's the thing that's meant to be strong, yeah? So, if I were to now take this object, I'm just going to draw it, and I would then put this onto a piece of plywood. I know by default, we're going to just lay this out on a piece of plywood so that it fits, yeah? You know, we've got our sheet of plywood, we lay it out, we just rotate it however we want so it fits, yeah? But if our plywood is traveling in this direction, the grain, we're actually going to make something that's counterintuitive to what we're going to construct. So what direction do we think would be optimum to make this work?
The other way.
The other way, yeah. So a grain like this would be good, but is it optimum?
No.
No. So what would the optimum grain be? Huh? But give me more than just diagonal. If we could control the grain in the timber, you know, specify exactly what we want, what would the perfect grain be?
As our lines are going.
Yeah. So the grain that follows the curvature, the ruled surface lines, okay? But there's no way they're going to make plywood like that because it would be wasteful to make your sheets of timber that way. It is possible to actually get this. Like if you cut the tree a certain direction, you could get this. And I'm sure some wacko somewhere in the world has actually tried doing that. Who knows, it might be me one day. But we can at least use the grain vertically, yeah? And then we can kind of encourage the timber to have its own grain, yeah? All grain in timber is, in section, is just little pieces of wood fiber that are just sort of like stitched together. Like they've got a fairly nice, strong relationship to each other, but they have bits of weakness in them and hence why, you know, when we think of grain, we're actually, we don't actually have any timber here.
Isn't plywood like cross grain anyway?
It is, but there's usually a direction to, like you normally get 3 sheets on the 3mm ply, and the one in the middle will be the opposite direction, but then your 2 main directions will be, I know what you mean. I'm just trying to get people to think grain-wise, okay? This is not the point being, the plywood grain isn't going to do the job for us, okay? We need to artificially create grain, okay? So if we think of grain as like having little gaps in the timber that allow, like as this bends this way, the timber can actually pull apart, yeah? Then if we look at this living hinge, see how it's like we've cut holes into the material, therefore allowing the material to flex as it bends, and therefore it's almost like creating our own like artificial grain, yeah? Cool. So in the case of plywood, yes, like we have to create an artificial grain for this to work, okay? If it were MDF, we would have to. And hence why balsa wood's such a nice little flexible thing for actually creating curves around corners. Cool. Okay, so we're going to make this pattern, okay? We're going to go back to Brain Cell Man. We're going to actually pseudocode this pattern up. So, I've got 2 lines. I've got a sheet of material that we want to create this pattern. Let's start coding it, okay? So can you guys start giving me an instruction to do this, to start making that as a group? Like, what would step number 1 be? It could be anything. Huh? We've got a box.
We get our lines back that we drew. Are we doing it to that, not these?
We're going to do it to this first, okay? Like on the board. Then we're going to do it to our actual surface in code.
Would you shatter your edges to get points?
Right, okay, yep, so we kind of want 2 we want 2 edges, yeah? Which 2 do you want?
It's going long ways.
Okay, the 2 horizontal ones?
Yeah.
So we'll just say this is edge A and this is edge B, yeah? So we've picked out 2 edges, then what are we going to do to them? Okay, Yeah, we could shatter them. Let's similar concept. Let's divide them. Yeah. So we'll divide them by a number.
List them?
Huh?
Do we then list the points?
Yeah. So the instant you divide these will list up. Yeah. Huh? Look, you've got the pattern in front of you, right? You just have to, you've got to get this looking like that. Join.
Then you drag a line between the points.
Right, so we create lines. Yeah?
Then you shatter those lines.
Okay, so we'll say, I'll just shatter them in half, okay? Just to save my time. Yeah? That's a shatter. So I'll draw that as a line. Yeah? Actually, let's do it in quarters. Yep.
Then you want to select lines in between, but I wouldn't know what command to do that with.
But so, are you? Would one like if we can?
Do what we did with finger jointing.
Right. So see these lines, right? Do we just don't want the odd ones or the even ones, right? But if I do this, right, I have to do that to everything based on what you guys have said. So I'm going to create this. Is that going to give us the outcome that we want?
You want
every other one, so you want to alter them.
Right, okay. So we've got a two-layered pattern type thing, right? So we want to do a process to...
Yeah, but I just don't know the command.
No, we're just talking.
Okay.
Yeah? Did I fuck that one up?
Yeah.
Yeah? Does everyone get that?
Yeah.
Do you see, so you see the pattern? You can see the pattern here. There's one extra step, which is we want to extend these lines a bit so that there's there's an overlap. You can see how these two don't line up. Like they're extended. Yeah? We can extend the curves, yeah? So, with that in mind, what's going to happen when we do that to this, okay? We've got a line here, yeah? But we're going to a point. Yeah? You get that?
Yeah.
There's a problem. As I laser cut to a point, anything that goes to a point is going to get infinitely close to each other, as it gets closer and closer and closer to the point, yeah? So as you get closer to this point, you're going to start to create a lot of heat, a lot of surface area, a lot of very thin material that will eventually begin to disintegrate, okay? And so it's probably best, before we go into the laser cutter, to actually go, okay, we know that this is probably going to end up looking like this, because that's just how the material is going to break down after we cut this thing. So why not just create that shape? Huh? Let's just end it so that it doesn't end up creating that mess, yeah? Because we don't want a messy end. Cool. So what we're going to do is actually generate a shape that looks like that. Cool? So just as a quick process, as we work on this, we got to get our surface to look like that. We're going to use this thing called isotrim. What it does is it takes a domain, a two-dimensional domain, and applies it to the surface. So we're going to grab isotrim. We're going to plug our surface into the S. We're then going to go to the maths section, and we're going to go grab a construct domain squared. Really?
Yeah.
Let's use the one that's just like a single square, not one that has like two things going into it. You can either do this one. Let's use the one with 4. So what this does is it creates a 2-dimensional domain. So in this case, it has a u direction and a v direction. Whenever we think of something other than the world coordinates, so be it like the face of a surface, or in this case this pattern system, we always think of the x direction relative to that as u, and the y direction relative to it as v, and the z direction relative to that as, let's go this way, w. Okay? And so those of you who have probably played around with 3D rendering programs, you'll be familiar with UV mapping, or you've at least heard it, or it's something that, like, it's just a way of knowing that we're talking about a relative coordinate system and not a world coordinate system, okay? So we can see here that when we create a domain, it's giving us an option for the start and end values of the u direction and the start and end values for the v direction, okay? So u being relatively the x and v being relatively the y. So if we plug this into our surface isotrim, reparameterize our isotrim as well, and I'm just going to throw a slider into the construct domain. Let's put it into u. We can see as we slide this up and down, it starts to give us the domain of the surface from 0 to the u percentage. In this case, we don't want u. We're going to instead then plug that into the v, and we're going to plug that into the v0. And so what that does is it trims it, and it's going to trim it to the point where we can choose it to trim back off that surface edge. I'm going to get into surfaces a bit further down the line about like how they work mathematically and stuff like that. Cool. So what that does is it basically cuts that edge off without us actually having to do a trim or anything like that. Like a physical trim, it's a isometric. Well, no, it's an isocurve trim using the parameters of the surface. Cool. Knowledge is power. You don't have to trim things the old way now. You can trim them using maths.
Mine doesn't go from the corner, it just...
Where does yours go from? The other side?
No, it just goes from...
Slide it up and down? No, that's not a slider. That's a panel.
It just does that.
No, your number slider has to go from 0 to 1.
From 0 to 1?
Yep. This won't work unless your number slider is from 0 to 1, because we're going from 0% to 100%.
So that's a silly question again.
Sure.
Reparameterize, what does it do?
Reparameterize makes something think of itself in percentages. So if you've got a line, it doesn't matter how long the line is, reparameterize makes the system think of the start as 0 and the end as 1. So the midpoint is
0.5.
Yep, 0.5. Yeah? So that not only applies to lines, but also surfaces. So this is something I will go over in the future, but a surface is always four-sided, always, okay? So if we think of the two sides as u and v, then reparameterizing makes the bottom left corner 0, 0, and the top right corner 1, 1 in the UV coordinate system. And so by us reparameterizing this, it's making us think of it as trimming from 0% to 100% of that surface. Cool? And even though it doesn't seem like it, this is a 4-point surface, a 4-sided surface. I said it doesn't seem like it, but it is. Okay, and the point being, if I slide this now up, how many sides do we have? Right, so our 4th side, let's say at this point, is half of the other side, the opposite side. How wide is it now compared to the opposite side?
0.
Yeah, it's 0, but it's still a side. It still exists, yeah? Okay, so we've made our isotrim, and we are now going to break our isotrim down. Actually, let's not use deconstruct. Let's use B-rep edges. And we want to pick out from these B-rep edges the naked edges, because it's a surface. It's only ever going to have naked edges. If it's a B-rep, it'll have more, but it's just a nice pure surface. We'll pick out the first edge, which happens to be the edge that we've just trimmed, okay? And if we're thinking in order, what would be the opposite side? If the first one is 0, what would the opposite side be?
2.
Correct, 2. So we'll just grab another list item and plug into that 2, and that'll give us the larger side. So I'm just going to hide everything except for those 2 lines, seeing as that's how we're just going to work on these 2. It's a lot less stressful than last week, right? Yeah. That's because we're almost done. We could be done by 11, maybe. In that case, we'll make this a little bit more special. One year I had a student give me like a pattern similar to this for their living hinge. It was cool. If you actually create patterns like this, like depending on the width of them, then you can actually generate 2-degree surfaces with plywood.
Does that not start a fire?
Well, yes and no. It's just very well controlled. So like you can stop. I don't think this would have created this. This isn't too dangerous for fires. The most dangerous thing for fires is that, like just generating the same line over and over and over again, and then cutting it. And because a lot of people, they don't see, you can't see lines on top of each other in a CAD package, it does that. So this is okay, this is fine. But this allows us to actually generate, you could actually generate a hyperbolic paraboloid because it allows this thing to stretch and shrink in multiple directions. But we'll get back to that. Okay, so we've got our 2 lines. We've all got 2 lines. Okay. We're gonna make a mistake and we'll fix it, okay? But I just want you to know a mistake's gonna happen. Cool? So, now that we've got our 2 lines, what are we gonna do? What did we get to? We had our 2 lines, our line A and our line B. We've got them here. What did we do to them?
Divide.
Let's divide them. Do you see why this stuff is almost just as important as actually knowing how to use Grasshopper? Like, is everyone getting that? Like, the actual thought process of how to get to the end result is more important than actually knowing the components that'll get you there? Yeah, okay. So we've divided the curves. What do we do then?
Join them.
Join?
Join the points.
Use a different word.
Create a line between the points.
Okay, and if we all now create lines, you'll see exactly what I meant by making a mistake. I'm not going to do it. I want you to discover the mistake.
They're not order.
Yeah, they're in a different order. So do we know why?
You're joining 0 to 0 and just going around clockwise.
Exactly, right? So if we drew a shape that was, a closed shape, and now we've extracted the curves from it. So this line here is going in that direction, whilst this line is going in the opposite direction. Does that make sense? So there's two ways that we can fix this up, right? We can either flip this line so that it goes the opposite way, or we can take the points that it generates and reverse their order. Like, we get the same result. So we could either use flip curve. So if we plug our second curve into that and plug that into the divide, it flips it. Or just so that you're aware of the other way, there is a list function called reverse list. And so if I were to plug the output of the divide curve into reverse list, then that would also generate the same result. Feel free to do whichever one you wish until I discover why we shouldn't have used one later, and then we go back and actually undo what we just did. Okay, so what did we do next? Okay, so this is where I'm going to pause you. If we go down that line of thought and we shatter them, we're going to end up with the shatter where they don't alternate, okay? So now that we've got the lines, we want to do one thing slightly differently to both sets of lines, right? We want there to be an alternating pattern. So at this point, I think we should dispatch them, okay? So now that we've got the lines, we're going to do something to all the odd ones. We're going to do something very similar to the even ones, but it's going to be a little bit different, okay?
My flip curve came up with this error saying recursive data stream pattern.
Really?
Yeah.
Did you do this?
Yeah.
Did you go, what are we doing? Ooh. So, yeah, I know. So guys, sometimes you might see an error like this. Come on. Recursive data stream found. What that means is that something in the script is going from right to left, okay? As we've seen, you've kind of got used to this. The inputs are on the left and the outputs on the right. And so if you ask something to flip and then flip again and then flip again and then do you see the relationship that I've set up here? I've asked it to flip, then flip, then flip, then flip. Like there's a loop there, right? Grasshopper doesn't normally allow for loops like this, and so it'll just warn you instead of going for infinity. Okay? So that's what that's doing. Cool? Okay, so we've got our lines. We want to break them up into two lists. So let's use a dispatch, and let's create a nice little pattern for our dispatch with a 0 and a 1. And what that'll do is send all of the even ones out to B and all the odd ones out to A. Oh, it's so close to being finished. So I'm just going to hide everything but the lines that we've just dispatched and the two end lines curves so that we can see them. Okay, so now what was the next step?
Shatter.
We're going to shatter them. Okay, and where are we going to shatter them? Because shatter requires more than one input. So where else are we going to shatter them? Is it Joe?
Yes.
So we're going to shatter them. We want to shatter them evenly, yeah? So if we use a range component, range gives us a number between, like by default, between 0 and 1. So what does that mean we should do to our curve to make sure that it is shattering based on percentages? If I want to shatter this at 10%, if I want to shatter this at 10%, 20%, 30%, 70%, 100%, what do I need to do to the curve to make sure that it uses percentages? Do you want to say it louder? Reparameterize. Yeah, remember? Yeah. Okay, so we're going to reparameterize our curve and we're going to plug our range into the shatter. The cool thing is it doesn't actually matter if we shatter something at 0 and 100, it ignores them. So we don't have to clean that up. And what that should do is it should create branches now. And fortunately, we don't have to actually consider them too much. Like that looks like a bit of a messy thing, right? We can see our wire is dashed. It's probably the first time you've seen a dashed wire. Like we just want it it's going to get a bit complex, okay? But that's fine. All we have to do is dispatch these guys a second time. And we are going to let's use the exact same pattern that we used for the first dispatch, okay? And the output that we want is, let's say, just the A. So the result of this is we get a dashed line. Just see this pattern that we used for the first dispatch? We're going to use the same pattern.
Yeah, mine's broken.
What do you mean?
It's red.
Which one is red?
The dispatch.
And if you mouse over it, what does it say? Mouse over the little red bubble that comes up.
Data conversion failed from text to Boolean.
Okay, so that means this guy here has got something in it that isn't a Boolean. Have you right-clicked the panel and made sure that multi-line data is off? Okay, is one of the lines empty?
Nope.
If you double-click into it, is there a space after one of the zeros and ones?
Probably just a Mac.
Yeah, I think it's a Mac.
Ah, okay. Then in that case, another way of doing this is getting a Boolean component. Is it happening to you too?
No, it's fine. Mine's fine.
Okay.
The
Grab a
only
book.
time mine broke was the cluster.
Right. Grab a Boolean component, right-click it, go set multiple Booleans, and in that type 0 and 1, and then select commit changes, and then use that instead. Is it working now?
Yeah.
Excellent. Okay, so everyone should have a dashed line. Yeah? Dashed lines, not just dashed line. Cool? Okay, so if we do the exact same process so I'm just going to slide the range out because we're going to use the same range. By the way, let's just quickly make a slider for that. So let's go from 2 to, 2 is less than 30. So we can control the number of dashes that we create. Woo! Ultimate control. That's what we want. Okay, so we're going to copy the shatter and the dispatch down, and we're going to do the same process to the B output from the first dispatch. Oops. But on the dispatch, just a quick little process that we can do to the pattern. If we right-click the P and select invert, what that does is it makes all trues falses and all falses true. So that means that when we get the A output of that dispatch, it's going to be the opposite of the A output of the dispatch above. Make sense? So we've now got an alternating pattern. We can control the number of divisions of our dash, and they will alternate from line to line. If we grab our divide curve, see the two divide curves that make up the line? If we create a number slider that goes into both, so one that goes into both the ends of that divide curve, as I decrease and increase that, that'll decrease and increase the number of divisions across the whole surface. If I do, so I put a number slider into these two divide curves. Yeah, it's just giving us a bit of control over the divisions. You can. Cool. Okay, so we've got a lot of control over these, but we've got to do one more thing, and that's extend our lines a little bit. Okay, and we're going to do that just by using this component called extend curve. We used it last week in the mess. You remember in that like chaos near the end of the tutorial we used it? Yeah. Okay, so what we can do is we can just plug both our curve lists. We don't really care about the data structure anymore. So we can hold shift and plug both our lists of curves into the extend curve, so we don't have to duplicate using that component. And we'll grab a slider, and that slider can be whatever you want. It's going to be relative to the dimensions that you're going to extend. So if, like, let's say we want to extend it by 20 mil with a bit of a tolerance. So I added 0 is less than 20.00. That way it's got, you know, a bit of decimal pointage in the millimeters. And if we plug that into the L and L1 of our extend curve, then as we slide that up, that will extend each of those lines by that length. And there's going to be a little bit like, you're going to have to gamble. If you're either going to have to spend a lot of money or gamble and be lucky. So this is what's annoying about making the laser cutter cost money to use, because you guys aren't material scientists and you're not experienced living hinge makers, okay? So you don't really know if the parameters that you've just set up are going to be the best parameters to make this flexible enough without making it too weak that it just breaks, okay? If you make the spacing between these too wide, then your plywood might snap. If you make it too thin, then your plywood might snap, okay? Fortunately, the length of each of these elements doesn't matter so much, but the more connections you have from one section to another will generally make the whole thing stronger, more robust, but still curvy, okay? But there is one thing that we want to do here that is not going to happen. Just like if we just go straight to the printer right now, this isn't absolutely perfect yet, okay? And can you guys tell what that is based on maybe that shape?
The cuts aren't wide enough.
Yeah, so what we're doing here is we're relying on the width of the laser, and depending on the machine that you use, normally laser cutters are prided on how thin their laser is. So it might be like 0.2 mil thick cut, okay? So we kind of want to actually encourage these to be a little bit wider, okay? And this is the dangerous bit, right? Because the width that we make something up here, if we then look at it down here, it might end up completely destroying the cut, okay? So just be careful with that. Do you wanna make like a little funky one? Like not just like a straightforward one?
Sure.
Okay, let's do it. Shall we? Okay. So what we're going to do, let's make one that looks like this, and we'll also round the corners off. Okay? There's so many ways to make these, by the way. Like they don't have to be straight. You could make them any shape you want, basically, just as long as they infer grain in the timber, it should work. So what we'll do is we'll just right-click the output of the extend curve and flatten it. Oh, one thing, guys. One thing that I kind of forgot. At the beginning here, when we generate our lines are always going to be generating on the edge of the surface, and we don't actually need to cut there. Okay? So one way of getting rid of the start and end point was, remember we used the shift list earlier, and that got rid of the start and end point. Another way is by using this component called cull index. Where are we? Cull index works very much like list index, but instead of picking out an object at an index, it's going to remove an item at an index. And if I was in a list, sorry, I can't remember your name, but the person sitting all the way down the end, hello. If we have a list and I want to get rid of the first and last item in the list, and I don't know how long the list is, what indexes can I use to pick out or remove the first and last item? You have no idea? Okay. Can you at least, what's the first index? Okay, so what's the second index? So if we go backwards from 1 to 0, and therefore from 0 to what? What's 1 back from 0? So the end of the list, the last item is exactly. So if we want to remove the first and last item, what indexes can we use? And no, that's 1 is the second item. Excellent. Good. By the end of this class, I'm going to say that so many times. So if we want to get rid of the start and end point, we're going to get rid of 0 and -1. And let's make sure that's a multi-line data list panel, sorry. Plug that into I, and now if we plug that into dispatch, that'll get rid of the start and end point, start and end lines, so that we don't potentially create a fire when we laser cut this thing. Cool? Okay.
Sorry, where did you put it into, sorry?
We did a cull index after these.
You put it into dispatch.
Yeah. Does everyone get why we did that? Cool. Okay. Imagine designing in this thing. You got to get really used to it before you actually do that. But that's kind of what the point of this is. Eventually, one of you might actually do that. Hopefully. We'll see. Okay, so we've got our extended curves. We've flattened them. Just make sure you've done that, because we're getting into the territory of crashing computers unless we don't flatten them. Okay? and we are going to create arcs. And have I asked you guys how many? So circles are planar, yeah. What else? What other shape could be planar? Like is guaranteed to be planar? Triangles. Okay. So there must be a relationship between circles and triangles somehow, right? So if I pick out 3 points. If I pick out 3 points, those 3 points can make a triangle, yeah? As well, those 3 points can infer a circle, yeah? If I add a 4th point to the system, it might not be on the circle, yeah? So circles can be defined by 3 points. Any other number could break it, okay? So in the same way, we can define arcs by 3 points. Cool? So what we're going to do is we're going to use the start and end point of our extended line to generate an arc. We're going to offset the line, get the midpoint to then create the curvature of that arc. We're going to do the opposite on the other side. And then we'll join them and actually fillet that arc, and we'll create little football holes. Cool? They'll just be like, maybe more like tablet. You know those like vitamin tablets? Be tablet shaped. Cool? Okay, so we can quite easily get the start and end point of our extended curve by using the endpoint component. That's that particular aspect of it done. Very quick. Then we want to take our curves, we want to get their midpoints and have that midpoint offset to generate the arc. So let's offset our curves, and we'll use loose offset just because of the way it deals with data. And because we're using lines, like very, very straight lines, how many planes can a line offset on? Like a straight line, how many planes can that be offset on? Normally we think of a plane, you know, when we have a line, we think of the XY plane, yeah? And that offsets on the XY plane. But if you've got a line, how many planes could it be offset on? Normally when I ask these questions, there's one of 3 answers, okay? One answer is 0, it can't be offset, right? But it can, we can see that it can be offset. The other answer would be 1, there's only one plane that it can be offset on, yeah? But we know lines can be offset on more than one plane, right? So then the third option normally is infinite. So there's an infinite number of planes that our line can be offset on, okay? In that case, Grasshopper goes, I don't know which one. Like, if there's an infinite number, which one do you want me to offset on? So if we plug a line into the offset loose, specifically lines, see how it's already like, no offset plane could be constructed from this curve because it's a line. That means we then have to instruct it as to which plane we want to use. So we want to offset it on the on the XY plane. So plugging XY plane into the P, that then gives us the offsets. Does everyone understand why I spoke about the infinite planes? Yeah? No? You don't understand why? You shook your head?
Yeah.
You don't understand? Okay. I'll explain it then. We've got time. We've still got an hour. Okay, I have a line on a plane, right? Like in 2D. So when I offset it, it's going to look like so, yeah? Like we're used to doing offsets like that. But if I have a line in 3D space, what plane does it get offset on? This plane? Yeah, but look, I can draw lots of different planes that line sits on, yeah? That line could be on infinite number of planes. They're just all, like, it's not every plane, but there's an infinite number of them, right? That rotate on that line. That line being the axis, yeah? So this component says, you've given me a line and you've asked me to offset it, but I don't know which one of those planes you want me to offset on. So you have to tell it which plane it needs. Does that make sense? Okay. We all good? I know, like, every time we go to like old school maths, things get a bit like glaze over. But yeah, got it? Hopefully this makes... Pardon? So if it's going red, it'll look like this. Yeah? Mouse over this little speech bubble. What does that say? Oh, okay. Yeah, you have to give up at that point. Okay, no, so what you should do is just make a little, so we're going to double click. I'm going to type 0.001 to create a number. Oh, no, we don't. Don't type 0.001. That's not a good idea. Type 0.002. That'll create a nice little number slider. Actually, that's probably not a good thing either. Drat. Type 1.000. Far out. I'm not used to these shortcuts. So what that'll do, is that now working now? If you plug that in? Really? Okay, in that case, please grab this other thing. It's called offset curve. Not just for you. Plug the curves into that, plug your slider into the distance, plug your plane in. Is that working? Pardon? Okay, just right click the output of that and select flatten. Okay, cool. Okay, so the only reason we've done that is huh? It's rotated. You mean it's going the opposite direction?
It's kind of like that.
Huh? Okay. It's just because this is such a large number. Look. Like, do you see? Yeah, you get it? You get it? Cool.
I don't have an offset here.
You don't have an offset?
Yeah, it happens one and then it just disappears.
Well, this is all off.
Yeah, because I want to see which parts gets wrong.
Pardon?
You can enable this part. I just want to see because I got the offsets before and then something just happened and then they were gone.
Okay, you've inverted it that way. That's cool. See this number? It's just too big, probably. No? Okay, that's not it. this number here, plug that into n. Hold Control Shift.
Okay.
Cool. Okay, get a number slider and plug it into D. What's going on here? Looks like, you've got a similar issue to her. Cool, okay. So all we're really doing is we're offsetting this purely, well, okay, for one, you could actually use these offsets to generate like a bar, like a rectangle that cuts, yeah? Like all you have to do is offset the opposite direction and then connect the two ends, and then you've got yourself like a little rectangle, yeah? But what we're gonna do is evaluate the length of our offset and get the 0.5 point of that length. And just to make sure that it's thinking about percentages, just to be sure, right click and reparameterize. Okay, so what that's doing now is we've got endpoints, the evaluated length at the midpoint, which means we've got 3 points per line, which means we have enough to generate an arc.
Sorry, where did you put the 0.5?
I put it into L, my bad. It's my force of habit.
That was quite basic, mate.
Yeah, so if you type 0.5 and plug that into L, that should work. Less stressful this week? Good.
Did it get harder than the last week's course? No.
The difficulty with this course goes like this. Like, week 3 is mental,
Yeah.
and then it gets better, and then it gets a little bit more difficult, and then it gets better. Huh? When we start screwing around with like booleans and like boolean functions and meshes and stuff like that. But it's just there's like everything that we do here gets repeated.
Next week should be.
What are we doing next week? What are we doing next week? Yeah. Next week is 3D printing. Next week I think we remake the hyperbolic paraboloid a different way. So it's a lot of just curves and surfaces. So yeah, it's quite easy next week. This week, like unwrapping a surface is something most people don't attempt. They go grab a plugin and they use that, and the plugin isn't always correct and it doesn't generate the outcome that they need. So in this, like we've done something that normally beginners don't do. We did that last week as well. Okay, yeah, like it's just part of the process of actually having to build this stuff. If we prioritized the skill sets to learn in order, then we would do finger jointing exercise last. But instead we've prioritized it based on the construction methods. It just doesn't, it's different. Okay, so we've done our offset, we've evaluated, we've got our endpoints, we've got our evaluate length. If we go to curve and grab the 3-point arc, arc 3-point, and we plug our start point of our line into A, our midpoint into B, and our endpoint of our line into C, that will then generate an arc on each line. Is it working? 3-point arc you can find here. next year, we are not doing it in these rooms. We're doing it in a big room with a projector. Or they just give us bigger TVs. Okay, so if we think about, yeah, what happened? Just zoom out.
It's like
You just skipped this one thing. Right-click the C output of offset and select flatten. What you were doing was this. Hopefully this won't kill my computer. Yeah? Is that what you got? Yeah. Okay, we're back. Hopefully you guys don't ever kill the computer doing that. You will, but whatever. Okay, so what we're going to do is we're going to copy our offset and our evaluate length and our arc 3-point. Copy it and paste. And actually we can use the same number slider for the distance of the offset, but we're going to right click that and we're going to change the number as it comes into the input, okay? So we can either do that outside, but there's this nice little shortcut that Grasshopper allows us to do, and that is if we right click an input and go to expression, we can type maths into that expression with the variable that goes in being x. So in this case, if we've got a number slider that's controlling this going one direction, the opposite direction is going to just be the negative of that, okay? So if we go negative x in that expression and select commit changes, that will then mean that when we plug a number into that, it will always be the negative of that number. So
plug that into
D, yep, so I right click expression and I type negative x into the expression. So that means as we run this number slider up and down, it's going to put a positive number into the first offset and a negative number into the other offset. This looks cool. Negative x. I right-clicked D, and I select expression, and I typed into that negative x. I will put this here. Nope. Cool? Are you getting what we want?
Yeah.
Excellent. So we're getting very weak down here, right? And we just want to make these little lozenges. So what we're going to do is join the curves. So we're going to plug our arcs, both our arcs into the joined curves. What that'll do is it'll look for all the curves that are actually touching end to end, join them as a single object. And then after we've joined those curves, we can throw in a fillet, which you can find under curve utility, in the same area that you get joined curves. So with that, if I plug in a number slider, so let's say like 1.00, if I plug that in and reduce that down, we start to create little lozenge shape things, like so. And so you might, like at this point, start playing with, having a bit longer lozenges, and the fillet in this case is the thing that's breaking us. So you just want your fillet to be rather small, or otherwise it's gonna, screw up your shape. But that gives you a nice little pattern that you can create across your living hinge. If you can somehow work out how to make the holes on the wide side wider and the narrow side thinner, you'll get a HD for this assignment.
Could you please scroll out a bit?
Sure.
What did you say?
If you can figure out how to script this to have the holes on the narrow side as thinner and the wide side wider, you guarantee HD for this assignment. I'll give you a blanket 100%. But that's all I'm saying. I'll give you 110%, actually.
Right, I'm starting to think this might not be worth trying.
Yeah.
Sorry, I don't have the round.
Okay, is that because you've... so what the thing that happens with fillet is if the number, like, if I want to draw a radius 1 edge on this, do you see this shape? I'll just draw a radius 1 circle. See how that just doesn't actually work anywhere on that shape? So in that case, if it doesn't work, it just doesn't fillet. So it's actually probably better to have a small number instead of a large number. Huh? Really small? Right, how small is it? If it's 0.05, just zoom in. Can you see, is there like a little edge to them? Like, do you get something like that? Or right click, just right click C and select flatten. Right, is the outcome of your drawing curves like a dashed line? Okay.
You won't allow me to connect both the arcs together and the joint curves. It just bumps one of them off whenever I do it.
What do you mean?
I've got the joint curve. I'm gonna try and go.
Hold shift while you do that. Cool. Don't worry about the fillet. That's just like, it's just a fancy extra, okay? The point being, the curves that we generate from the B-rep edges. So see the ISO trim, guys? Like if we go back to the beginning, well, halfway through the script, the ISO trim, after the ISO trim, we've got these B-rep edges. If we bake the naked edges into Rhino, and we bake the outcome of our pattern making and living hinge making, so we bake them into Rhino, then this shape here is the one that we would laser cut. Okay?
I can only put one half into the joint.
You can only hold shift when you drag the other one in.
So for this assignment, we want to do this 5 times, so we've got the same.
Or 6, or 3, or whatever.
So it makes the.
But just remember, some people here have different designs. So you want to configure this for your design, yeah? So at the moment though, just remember as well, I've done this only for the surface aspect that makes up 1/2 of our hyperbolic paraboloid, okay? We will have to copy and paste all of this for it to then apply to the external point, okay? Does that make sense? Okay, I want you guys to think critically on that one outside. Like, you'll work it out. It's pretty straightforward. Cool? Hooray, we've got half an hour left to shoot the shit. Yeah. You have a bunch of questions.
Yeah, because like they have like right line from many components.
Pardon? They have what? Just maybe bring your laptop down and I'll have a look. And then maybe it's a problem that I can show other people as well. We've got a whole bunch of empty lines, empty components.
Yeah, it starts from here.
Okay, have you ever tried dividing something, like if you want to create an even number of points, even number of segments across the line. So I want 5 segments. I want to take a line and divide it into 5 even segments, yeah? Or 4, sorry, so, no, 4. 1, 2, 3, 4, yeah? Okay, what's the lowest number I can get? So if I do 3, it does that. Yeah, if I do 2, it does that. If I do 1, it does that. Can I go any lower than 1?
No.
And what are you asking it to do?
Oh, it's 0.25. So it's
So when you round that, what will it round to?
to 1 point.
No, rounding. When I round a number, we round up after 0.5, and anything below 0.5 rounds down. So what's your number going to round to?
Oh, round this way.
Yep, so what would that round to? 0.25 rounds to what?
To minus.
No. So if I've got 2.6, what does that round to? It goes up, so what does that become? If 2.6, 6 is above 0.5, so what does that become?
So it becomes 3.
Yeah, okay. 2.4 becomes what?
2.
Right, so 0.25 becomes?
0.
Yeah, so if you divide something by 0, what do you get?
Nothing.
Yeah.
Okay. So just turn this to 4.
Yeah, but your slider can only go to maximum of 1. Okay, is it working now? Yep,
Yeah, it's working.
excellent. Got it? If you divide by 0, it doesn't work. Breaks.
Oh, okay.
Because if you can't divide anything by 0.
So the minimum number is like 0.5. This will go to like
0.5 is when things round up. 0.4999999 recurring is rounding down.
Okay.
Cool. Yes. Come on. Do you want to swap with this dude? Oh, okay. Do you see how you don't have your alternating? What's going on here? Using the wrong fillet. By the way, just check the alternating pattern. Make sure, try and get it to alternate, man. You work it out.
Honestly,
Hang on, in here. Invert that. Right click the P. Invert. Invert. Yeah. Ta-da!
thank you.
My new power cable. Okay. I'm gonna, guys, are we happy to stop recording now?